We'll proceed in pseudo multivariate calculus and we will validate our length vector and we will validate our. Okay, so in conclusion phase, we will validate our length vector. So nicely we are making dialogues so nicely that we are making dialogues that our length vector is nothing but that is I plus dy by dx j in bracket close dx. This is called length vector. Wherever you need length, just replace it with I plus dy by dx j into dx. Okay, the pseudo multivariate calculus, it is going to change the world in a way that I am seeing in the machine learning and artificial intelligence book, especially in the Bayesian theorem, from the very renowned authors we are saying in the book, the calculus that is mentioned in the artificial intelligence books are wrong. This is what I am seeing. So person must understand the concept, what is required. Person must understand the concept behind the pseudo multivariate calculus. Pseudo multivariate calculus means what is the idea of bringing calculus. Anyone would have the, I believe, same thing in the mind. What is the idea in bringing the calculus? Okay, generally people start doing the calculation with delta x, delta y by x, and then delta x tends to 0, and then let consider that this is the curve, but when delta x tends to 0, it will be a straight line, and consider that for infinitesimally small distance, then it will, the curve will look like a flat surface. This calculus is not that. Mathematics is not approximation. This should hit anyone's brain that is highly required. Mathematics is not approximation. Anything else can be approximation. Mathematics is exactly concrete thing, the completely qualified thing, and mathematics is away from approximation, and mathematics is full-fledged fixed calculation, even in the infinitesimally small region. So that's why we go with the primitive calculus, the calculus at which the calculus, the mentality of the calculus that was invented. I believe calculus was invented by Sir Isaac Newton, and the mentality through which the calculus was invented, that concept came as through the integral calculus. Nowadays, in modern calculus, the calculus starts from differential calculus only, delta y by delta x, where delta x tends to 0, and then calculus starts. Calculus is nothing but calculation of multiplication through graphical way. That is calculus. That's it. If I have repeated repeated addition can be, if I have 3 addition, 3 plus 3 plus 3 n times, then rather than making 3 I can write as 3 into n. This is called multiplication of two items. Multiplication is not a real entity. It does not exist. The existence in the real entity is is addition. Subtraction, multiplication, and division, these are considered as helper to addition. Main is addition. In a way, repeated addition becomes multiplication. Repeated addition becomes multiplication. That is one thing. And then multiplication that is computed through graphical way becomes integral calculus. Why integral calculus is important? Why not multiplication? Multiplication is good for multiplying two items when they are independent to each other. Like 4 into 3, they are independent to each other, that is 12. Y into x, they are independent to each other, that is yx. X square into x, that when they are independent to each other, then it is x to the power 3. But y into x, when y is dependent upon x, what is dependent upon x? Anyone would ask, what do you mean by dependent upon x? Y is dependent upon in this, x means y is a function over x, that is y equal to x square, means as you keep changing, I have two things to multiply. One is y and one is x. y is function over x, means y equal to fx, function over x, and y equal to x square. If that is the case, y equal to x square, then I am multiplying x square with x. Okay, it is not that straightforward, because as x is changing, y is also changing. Okay, they are not independent to each other. As if x is 100, at that moment y is 100 into 100. When x is 10, then y is 10 into 10. So if I'm multiplying y into x, y will keep varying when x will vary. Since it is algebra, so x is a variable and it will have different numbers. As x number is changing, y will also change. Y is dependent upon x. In that sense, x square into x will not be x to the power 3. X square into x will be x to the power 3 by 3. From here, calculus enters that you cannot multiply two items when one is dependent upon another in a normal multiplication way. You have to go by the area methodology. Area methodology is a way to calculate the multiplication of two items. If two items are independent to each other, if I am multiplying y into x, and x denote x-axis and y denote y-axis, and they are independent to each other, then it will form a rectangle. Make sense? If I calculating 4 into 3 through graphical way, if 3 is horizontal and 4 is vertical, it will make a rectangle. If one operand is independent of to another operand and operator is multiplication, then in the graphical way it will form a rectangle. An area of rectangle is nothing but the multiplication. Calculus proceeds in that, say indeed area of any multiplication of anything is area only. Just draw the area graph, calculate the area, that is the multiplication. If I am calculating x-axis and y-axis multiplication of y by y with x, then through graphical way calculating the multiplication of any two items is draw the graph first and then calculate the area of the graph, and that the area of the graph, and that will be multiplication. This is what multiplication talk about. Okay, this is what calculating multiplication through the area of the multiplication through the area of the graph. If I am saying y into x, x is x axis, y is y axis, x is x axis, and y is y axis, and if I draw a graph, then y is dependent upon x, then still multiplication of y into x can be calculated through the area of the graph. This is more consistent than normal multiplication. If I say y into x, where y is x square function over x, then if I go with normal multiplication, then x square into x will be x to the power 3. But if I try to calculate x square into x in a graphical way, then this is x axis and this is y axis, and y equal to x square, then it will give this kind of shape. X square will give this kind of shape. The area underneath is actual multiplication, that is x to the power 3 by 3. Okay, so integral calculus say when you are multiplying two items, then draw a graph. Calculate the area, that is the multiplication. Even if it is constant, 5 into 4 means on x-axis it will be 4, on y-axis it will be 5. It will be a rectangle. Calculate the area of rectangle, that is 5 into 4. This is what integral calculus is saying. Better way of multiplication is calculation of the area in a graphical way. That is the better way. If I try to find everything, every multiplication through graphical way, then that is called integral calculus. That is more prominent. Okay, now there comes vector also. When you are doing any calculation, insert direction there also. That is more meaningful. This is what vector is saying. So upper layer of the algebra, when we calculate multiplication, then it is integral calculus. Upper layer of algebra, when we are calculating the any computation, then we go with a vector because it talks about direction also. Anyway, these are considered as the basic concept of the calculus, why calculus comes into the picture. Calculus is is replacement for the multiplication. Calculus is more appropriate and more genuine multiplication. Okay, so calculus is not a competitor to multiplication. Calculus is complete multiplication. If it is dependent and independent concept comes, then also calculus works. Anyway, we have devised a kind of a fundamental, if people remember, called length vector. If I'm trying to find the length of a line, okay, if if I'm trying to find the length of a line, if this is x-axis, if this is x-axis, and I'm trying to find the length of a line, if I'm trying to find length of a line, then this is the line, length of a line from point 0 comma 0 to point x comma y. Then someone would say this is x-axis and this is the line. Then someone would say 0 comma 0 to x comma y, the length of the line is Pythagoras theorem, 0 comma 0 to x comma y, that is x square, x minus 0 whole square plus y minus 0 whole square root. That is the length of the line. If that is the length of the line, okay, length of a line, this is a line from section origin, one point that is origin, it can be anything, alpha, beta to x comma y. If it is origin and x comma y, the distance is Pythagoras theorem, that is x square plus y square root. Then we went that it is exactly same as the, if I represent this line connecting origin and x comma y through vector, then it is exactly the magnitude of the vector. And it is good that we go up. Means if I'm trying to do normal multiplication, better to do it through integral calculus. If I'm trying to do anything with Pythagoras theorem, better to do it with vector, because it is a more complete one. In that sense, if I represent a line through a vector which is connecting origin and x comma y, vector is xi plus yj. If that is the case, then magnitude of the vector is x square plus y square root. Same thing. Means if I want to find the length of a line from a point origin to point x comma y, then this length, this vector, if I represent this as a vector, then it will be xi plus yj, and magnitude of the vector will be square root of x square plus y square. Means if I want to find the length of a section of a line from origin to x comma y, better represent it as a vector and calculate the magnitude of the vector. You get the length of the line. So pseudo calculus says that if you need length of any line, represent it as a vector and calculate the magnitude. Then we saw that can we apply in this line, fundamental in this line, where we are connecting origin and another point called x comma y. This point is x comma y. This is x-axis. This is x-axis. This is a line curve. Equation is y equal to x square. It can be anything. Y equal to x cube or whatever it is. If this is the origin, this point is origin, and this point is x comma y, then through our fundamental, if I represent this curve as a vector, then calculating the magnitude of this curve will give me the length of this vector. Can anyone find the length of this curve from origin to any point x comma y when equation of this curve is y equal to x square? I know. Okay, represent this curve as a vector and calculate the magnitude of vector, you will get the length of the line. How to represent this curved line as a vector? If I represent this x comma y and origin as a vector, then it will be a straight line connecting origin and x comma y through vector. It will be a straight line. If it is a straight line connecting origin and this vector, then calculating the magnitude of this vector will be magnitude of this straight line rather than this curved line. Then we saw that what is difference between a straight line and curved line. For curved line, this at any point if I take x comma y by x, y by x is variable. Whereas if I take a straight line, then y by x, any point y by x is constant, same thing. Okay, in that sense, this is the only difference between the straight line and curved line, where in the curved line, y by x is different, where in a straight line, y by x is constant every moment. Now, whatever the vector representation we have made for a line xi plus yj, I'll make sure that there will be y by x exist, so that we will capture the variable part, that is y by x. If that is the case, then if I take out x in xi plus y, if I take out x, it becomes I plus y by x j, bracket close into x. Now y by x is coming into the picture. This is vector representation of a curved line or any line. Straight line is a form of curved line only. Okay, is a special case of a curve, straight line. So what is the vector representation of a curved line? It is I plus y by x j, bracket close into x. In calculus, if numerator is dependent upon denominator in division, it becomes differentiation. And if I multiply two items and one item is dependent upon another item, it becomes integration. Okay, please watch our previous video, it will take long time. Then it becomes now I plus y by x will become dy by dxj, bracket close, into x, that will become this I plus dy by dxj whole multiplied with the x. X is independent component, then full will become I plus dy by dxj, bracket close, into dx, into dx. Okay, so that is the concept of the vector representation of a curved line. What is vector representation of a curved line? That is I plus dy by dxj into dx. If I calculate magnitude of this, will it give the length of the curve? Certainly. This is our fundamental of pseudo mathematics calculus, pseudo multivariate calculus, because we start everything through very small thing. We started calculating the line length through Pythagoras theorem, and slowly we came to a region where now we have a solid concept that any line vector can be represented as I plus dy by dxj into dx. Now, can we validate this? Are really true? Okay, to validate this, we came to a concept called line integral. Line integral means force any vector field. If I integrate with the line, then it is called line integral. That is heavily used in energy calculation. Force vector dot product with the length vector is the energy. If this is the force vector and there is a curve, like this. If this is a force vector and there is a curve like this, and there is an item that is pierced in this curve, there is an item, there is a pierced in curve, and there is a force field like this. Because of this force field, this item start moving like this in the curve. What is the work done by this force field? What is the work done by this force field that it made this item move in a curved line like this? That is the question mark. Now, energy calculation work done is force field dot product with the force vector dot product with the displacement vector is the energy calculation. Now, question arises is, what is displacement vector for this curve? If I use my multivariate calculus, then force vector dot and then I plus dy by dxj, bracket close into dx, is our length vector. Just directly do it and get the result. Then, miss, someone can try. Calculating energy, force vector dot product with displacement vector. Displacement vector is nothing but line vector. If that is the case, force vector dot product with the displacement vector. If displacement vector and displacement vector, our displacement vector equation is I plus dy by dxj, bracket close into dx. This is our displacement vector. I plus dy by dxj, bracket close into dx. This is our displacement vector. Force vector, that is f1i plus f2j, dot product with I plus dy by dxj, bracket close into dx. This will give the work done. But anyway, Let's go through the traditional way and see if we are correct or not. Now, how to find displacement vector through traditional way? That is a big question mark. Okay, now traditional way say that if I'm trying to calculate the energy calculation of a force vector, if this is a force vector, what is the force vector? If I say force vector exists in xy plane, this is x axis and this is y axis. If force vector exists in xy plane, it will have x component and y component. So force vector, capital F on top of it arrow mark, capital F on top of it arrow mark. This is typically called force vector. Now force vector I can write as F1I plus F2J. F1 vector, F1 on top of it vector, oh, I'm sorry, F1I, I is a unit vector plus F2J. F vector can be represented as F1I plus F2J. This is the force vector. F1I plus F2J is the force vector. If this is the force vector, then force vector into displacement vector is the work done. Now, if I take this line, consider, okay, consider this is the line and this is falls in xy plane. If it falls in xy plane, consider this is x-axis and this is y-axis. This is origin and this falls in xy plane. I take any point here at x comma y. I take any point here at x comma y. If I connect x comma y from the origin, then this is called position vector. If I take x comma y here, if I connect x comma y here through a straight line, then this is called position vector. If I take x comma y here, if I connect from origin, this point, this is called position vector. So position vector can be many, depend upon which point I am taking. Connect from the origin, and that will be called position vector. I know position vector. If I am trying to find the work done when item is moving along this line, then any point I take here, that is x comma y, if I connect from origin, that is the position vector. Straight line, that is the position vector. Okay, I don't have a straight line longer than this. Okay, I'll bring. Okay, so that is the straight line. If I make it little more round, then this is the vector. Position vector will go like this from origin. Okay, if this is the position vector, then position vector is not a vector that represent this curve line. Position vector represent a line that connects origin at any point x comma y. Any point x comma in this y. If I connect from the origin, that a straight line is position vector. If a straight line is the position vector connecting from origin to that point, then if I now how to calculate work done? Force vector dot displacement vector. If I say force vector dot position vector, that is not the displacement vector. What is your displacement vector? Displacement vector is the vector that is along the line. If this is the line, the tangent at this point is the displacement vector. This is displacement vector. This is displacement vector. This is every moment of x comma y on the line, displacement vector is exactly tangent at that point. It is a set of vector, that is displacement vector. If this is the point here, x comma y, if I draw a tangent line, then this is displacement vector, tangent line. But if this is x comma y, if I connect from origin, then this is connecting this is called length vector. Okay, I should have brought a longer line. Okay, I believe this is longer line. Now, if I connect like this, then this is position vector. If this is the point x comma y and this is origin, then this is called position vector. Whereas tangent at this point, same point x comma y, this is displacement vector. If I keep changing x comma y, position vector will keep changing. Position vector will keep changing. Similarly, tangent vector will also keep changing, whatever it is. When I am talking about algebra, anyway it is variable. Algebra is anyway variable. If that is the case, algebra is anyway variable. then force vector dot position vector is not the work done. What is work done? Force vector dot tangent vector is the work done. Okay, in mathematics we call differentiation of position vector gives the tangent vector. Just take it for granted. Displacement vector dot displacement vector, if this is the position vector, if this is the position vector at this point, if I differentiate this position vector will turn into displacement vector, tangent vector. This is inherent nature of position vector. There is nothing called inherent, we have to prove it. Okay, so if this is the position vector, if I calculate differentiation of this position vector, then it will become tangent vector at this point. This is position vector at point x comma y. If I calculate d of p, that is position vector, it will give me exactly tangent vector at that point. If this is the position vector, if I differentiate this position vector, then exactly at this point it will give me tangent vector. If this is the position vector, if I differentiate this position vector, exactly it will give me tangent vector. This is what I want, tangent vector. Means d is differentiation. D of p, position vector, gives the tangent vector. This is what I want. So energy calculation is force vector dot product d of p is the force vector, is the work done. But we said work done is force vector dot displacement vector, and that is I plus dy by dx j bracket close into dx. This was through our multivariable pseudo calculus. But this is the actual calculus that is written in the book. Force vector dot with position vector will not give the work done because position vector is not along the curve. Force vector dot with d of position, d, small d and p, that is position vector. P and on top of it arrow mark, position vector. Force vector dot d of position vector, differentiation of differential position vector, that is displacement vector, will give the actual work done. Then what is position vector? That is xi plus yj. D of xi plus yj is dxi plus dyj. Then force vector, that is f1i plus f2j dot dxi plus dyj, will give the net energy calculation, that is f1 dx plus f2 dy will give the net energy calculus from the line that is 0 comma 0 to point x comma y. Integration, now it is dx dy, right? So integration from point x1 y1 to point x2 y2, and then f1 dx plus f2 dy. These kind of explanation are not available in any of the book. Anyone can try. Okay, now if this is the work done, f1 dx plus f2 dy, then what happened to our pseudo mathematics, pseudo multivariable calculus? There we said any length vector. If this is the line vector, any line vector can be represented as I plus dy by dx j into dx, because we started with xi plus yj, then I took out x from there, and I plus y by xj bracket goes into x, and then division will become differentiation and multiplication will become integration as per the primitive calculus. Now let's say try again. Now if we try here, if we try again, then force vector dot displacement vector, that is I plus dy by dxj bracket close into dx. If I bring dx inside, then it becomes dxi plus dyj only. Okay, same thing. Force vector f1i plus f2j dot product with dxi plus dyj. Okay, or dot product with I plus dy by dxj bracket close into dx. That is the vector, length vector in our concept. Okay, if it is a length vector in our concept, if I go by that also, then it becomes f1 dx plus f2 into dy by dx into dx, that is f2 dy only. Means our length vector concept that we calculated through multivariable calculus, is pseudo multivariable calculus, is intact, and it works with the normal work done fundamental. Now question arises is, can someone prove that the differentiation of position vector is indeed a tangent vector? Can someone prove? Can someone take it as an assignment? Assignment. Can someone prove that if I have a position vector, if this is a, consider there is sinusoidal, up, 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 up. Consider there is a sinusoidal wave. This is a sinusoidal. Now at the origin, hope this is this. I'm sorry. If this is origin, then this is a sinusoidal. This is this is pi and this is 2 pi, and this is here pi by 2 and here it is 3 pi by 2. It is a sinusoidal. If I talk about position vector, if I take origin, then position vector any point x comma y, then position vector will move like this. Can someone see? Position vector will move like this from the origin. Okay, it will cross the pi section and then hope, it will proceed in the beyond pi also. This is position vector will start from here and it will pass like this and it will go like this and then it will go like this. But if we talk about the displacement vector, or then it will go tangent to this vector. This is displacement vector. This will go tangent to this vector. Okay, everywhere tangent to this vector. So tangent tang, tangent to this vector. Okay, tangent to this vector. This is displacement vector. All along the line that is displacement vector. Whereas position vector is one end of the vector, it is sticking at the origin only. This is position vector. One end will always be at origin and another end will start moving like this. This is position vector. Whereas this is tangent vector. This is actually line vector that is tangent at every point. Can someone prove that differentiation of position vector? If I differentiate this position vector connects point origin and any point x comma y. If I differentiate this position vector, indeed it will become a displacement vector that is tangent at that point. Can someone prove it? If this is position vector, differentiation of position vector will give the tangent vector at that point. If someone really prove it, then our pseudo mathematics fundamental is intact. Anyway, it is intact. But our fundamental of the fundamental written in the book that work done is force vector dot d of position. Why it is d of position vector? Because d of position vector gives the line vector. So along the line, how much is the work done if item is moving along the line? If this is the line, this is x-axis and item is moving along the line, like this because of this force field, then force field vector dot product with this line vector is the work done. Okay, then that is d of position vector. Position vector is, if this is origin, then this is position vector. Everywhere position one side will be fixed and this is position vector, where a line vector is tangent at this point. To get the tangent at every point that is a line vector, you have to do d of position vector. How d of position vector brings tangent line, that is a matter of concern that we will prove and will take example of. Later we'll move on the, this is called line integral. We'll move it to surface area integral, and we will see what we showed as our pseudo multivariate calculus. In that we took the line vector concept, and through the line length vector concept, if someone remembers, we proved the area of a surface, volume of a surface, so many things we did. Can we prove this through the traditional way also? And we'll see both are same, so that we will see. Please do not mind supporting us. +91 is the India country code. 9483160610 is the telephone number. +91 is the India country code. 9483160610 is the telephone number.